In this video, we're going to discuss salts and do an example for the pH of a solution of a salt. So let's do salts to start with, just the basic concept. So salts are produced by neutralization. And neutralization is kind of an awkward word because it's sort of implying neutral, but what it really means is it's the reaction of an acid and a base. So at its heart, there's an H+. We're looking at it from a Bronsted-Lowry point of view. There's an H+ that the acid's producing, a base that the OH that the base has managed to produce by its taking of a proton from something else, and those are getting together and making water. So that's why you often hear this rather sort of simple mnemonic, which is that acid plus base gives salt plus water. Now, the important thing to remember is, whilst this is also what happens in a titration, we sort of play around with this until we get equal amounts of each. When we're talking about salt solutions, we're basically already over here. So we've finished. Now, that's a very important thing to remember, because what it means is you only got this, you don't have any of this or this to start with. And so this is the solid material that we're going to think about putting into water and then trying to decide what pH it is. Now, it's very important to be able to work backwards. If you've got the formula for the salt, you have to be able to figure out what acid and what base made that salt. Because in order to figure out what the salt's going to do, what is its pH going to be, you have to know what the acid and base parents were like so that you can figure out what's going on in the salt. So the best way to do that is to have these memorized. Memorize the 7 strong acids. Okay, so you have your 7 strong acids. You've got hydrochloric, hydrobromic, hydroiodic. Then you've got your perchloric acid, chloric acid, and your nitric acid. And that brings us up to 6. And then, of course, we have the kind of weird one, which is sulfuric, which is diprotic. So there's your 7 strong acids. And the reason why you've got to remember that is because when they are fully neutralized, this one has 2 protons. So when they're neutralized, you basically are going to break these pieces off. So you're going to think about the fact that there's all of these different anions that you need to be able to recognize. So, minus, 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 and then this is 2 minus because there's 2 protons. So you have to be able to see these species in a salt in order to be able to identify that the parent acid was one of those 7 strong acids. And you also need to memorize the strong bases. These are a bit easier to memorize because it's basically all group 1 hydroxides and some of group 2. So that's basically calcium, barium, and strontium. So what does that mean? When you see those in a salt, what you're going to see are going to be things like Na+, potassium+, etc. for group 1, or you're going to see things like calcium 2+, barium 2+, strontium 2+ in the salt. So once again, the charges aren't going to be there, but then the symbols will be in there. So you've got to be able to recognize that. So basically some combination of these with some combination of these. That's a lot of combinations, but if you memorize the base acids and bases, the parent ones, if you see anything other than that, it's a weak acid or it's a weak base if it's not on this list. So that's very important because, of course, strong acids and strong bases, they have 100% dissociation and they form spectator ions. And these do nothing in water. They just sit around and watch. And what do we mean by doing nothing in H2O? Well, remember you've got this going on. This is going on by itself normally. That leads us to our Kw idea. And if these are doing nothing in water, then they aren't messing with this at all. So what happens is you end up with neutral pH for the salt of a strong acid and a strong base. As an example, let's just take one of these up here. Let's say, for example, we take potassium hydroxide and let's add it to, let's see, nitric acid. There's my reaction. What are we going to make? Slight angle here. What we're going to get is we're going to make water and we're going to make potassium nitrate. So this is the type of salt we're talking about. Strong acid, strong base salt. This is going to have a pH equal to 7. I don't need to do any math. And the reason is because K plus and NO3 are spectator ions. They're going to do nothing. They're not going to interfere with this at all. So if you can recognize you have a salt of a strong acid and a strong base, you just know that it's a neutral pH. Where it gets complicated is if one of your parents, either your acid or your base, are weak. Now we'll cover weak with weak. Well, we'll talk about that a little bit in class. It's not something we're going to do in detail mathematically. So let's go ahead and do the second example. The first one is actually in the class to be done. So the one we're going to do is the second one. And what that one is it's sodium hypochlorite. So here's NaClO, and it's 0.1 molar. And we're going to find pH, we're going to find OH minus, we're going to find percent hydrolysis. So this is going to illustrate a whole bunch of different things. So again, the way you want to do this, as stressed in class, is go through the sort of decision tree. So what is this? Okay, it's a salt. It's not an acid or a base. You don't see any hydroxide, you don't see any hydrogens in there, so it's a salt. So what it is, it's a salt of, so break it into the two pieces. At this point you should be able to see those ions in there. So if we break it apart, we're going to have that. So this is Na plus, and this is ClO minus. So this is the salt of NaOH and HClO, which is hypochlorous acid. So now you can go back to your list and go, what kind of base, what kind of acid? This, hopefully you remember, is a strong base. This is a weak acid. So now you've characterized what type of salt it is. So now we can start figuring out what the salt's going to be doing. Since this is a strong base, when we get down here, this is what we assume is happening. We've just taken this stuff as a solid and we put it into water. So what is it going to do? First thing it's going to do is fall apart. It's soluble, so we're going to get the sodium plus ion. I'm just going to add the AQ here. And we're going to get, whoops, ClO, let's make that right, ClO minus, and that's also aqueous. So that's what happens when you first put it into the water to make the 0.1 molar solution. Now we decide what's going to happen here. This is going to be a spectator ion. And the reason it's a spectator ion is because NaOH is a strong base. So what we can now do is ignore it. As soon as you've identified you have a spectator ion, you don't have to worry about it anymore. It's not going to do anything in water, it's just going to hang out. Now we look at this one. This one is not a spectator ion, and it's an anion, so it's the conjugate base of HClO, which is a weak acid. So this one is going to do something. And when we say going to do something, what we mean is it's going to hydrolyze. So it's going to do something. And the most important thing to remember at this point is this is what you have in solution. This is your major player. This is literally just broken apart. So you've got a liter of solution, you've got 0.1 moles of this, which we don't care about, and 0.1 moles of this. That's what we have. We don't have this. That's how we made the salt, but we don't have that anymore. It's already done and reacted. So we started off with this solid. And so therefore, this is what we worry about doing something. When we set up our rice table, we're going to base it off of this. It has nothing to do with this, because the only way this is going to exist is if this does something in water. That's the key point. The problem is, guess what you're going to get given in the question? You're going to get given the Ka for HClO. And that's what tends to make people have a problem, because how do you know what's going to happen? The problem is what you need is Kb. So that's the problem. And you see why you need the Kb? Because this is what you have in solution. So this is going to do something, and it's not capable of being an acid. It has no protons. So it has to pick up a proton, which means we need to use a Kb expression to describe that. So in an earlier part of the material, we covered how we would calculate that, but basically it's equal to Kw over Ka for this acid, and it comes out to be 2.9 times 10 to the minus 7. Okay, so the original Ka was basically the opposite of that. It was Kw divided by this. And you can see again, that's the whole idea. A weak acid has a weak conjugate base. Maybe a little less or a little more weak. It just depends from this relationship how much. So now we're going to say what's going to happen. So this is what we worry about. Not this, or this. It's this. So what are we going to do? Well, if it's going to act as a base, Bronsted-Lowry theory says we need to put water in there to make this work. So we're going to do this. Let's do a double-headed arrow. So look, we do actually form, Cl is hard to write neatly, we do actually reform some of the original acid, but it's only when this starts to react with water. And then of course we have OH minus afterwards. So this is our R for our rice table, and this is the problem. If you start out with this instead and write out the Ka expression and show it acting as an acid, you're going completely in the wrong direction, and I guarantee you're going to get the wrong pH. So this is what you want to start out with. So now we have the rice going in. And now this is where it starts looking very familiar, because you can go, oh, okay, well, this doesn't matter because it's the pure liquid. This is going to be approximately 0 because in water we would have a small amount, 10 to the minus 7. This is 0 because it's only just been put into water. This salt's only just been put into water. So this is my 0.1 molar. And so it looks just like what you've done before. It should start looking like a problem where, say, calculate the pH of 0.1 molar ammonia. And in fact, it works out just like that, just has a different K. So the problem isn't so much the rice table, it's getting to the correct rice table, and then you're okay. We have minus x plus x plus x, 0.1 minus x, and x. Let's write out our Kb. It's going to be this. All right, so this is the conjugate acid of that base. OH minus, those are our products. And there's our reactant, ClO minus. Okay, H2O doesn't show, of course, it's just 1. And this is 2.9 times 10 to the minus 7. And all we have to do now is substitute in the numbers. So we have x times x, so that's going to be x squared over 0.1 minus x. And, oh, look at that, 2.9 times 10 to the minus 7. So we can do the approximation. That's going to be okay. So we come down here and we knock that out, and then what we can do is solve to get for x. We don't have to worry about the two roots because we're not going to worry about a quadratic here. And what we get is this: x equals, let's make that look like an x equals 1.7 times 10 to the minus 4 molar. And so that gives us several things. Gives us those two things, and then it enables us to calculate this. So what do we have now? We have the HClO minus concentration, 1.7 times 10 to the minus 4. molar. We have the OH concentration, 1.7 times 10 to the minus 4 molar. Notice that is bigger than 10 to the minus 7. So we know it's going to be basic. And then we have our ClO minus concentration. Oh, sorry. Yes, ClO minus concentration, the 0.1 minus X, which is basically going to be 0.1. Because if you take that away from 0.1, you get 0.1. All right, so that gives us enough information to finish the rest of our calculations. So some of them are pretty quick. If we've got all that information, the first thing we can do pretty quickly is we can do something like POH. So if we do that, our POH comes out to be 3.77. Now, remember this is POH, not pH, so it should be less than 7. And then we can use pH plus POH equals 14, and that gives us that the pH is equal to 10.23, basic. So why is it basic? It had nothing to do with the sodium hydroxide. Let's go back up here and have a look. Nothing to do with the sodium hydroxide. It's basic because our hypochlorite ion hydrolyzes, that means reacts with water, forms this acid, a small amount, not a lot, and in doing so produces some hydroxide. And even though it's not very much, compared to the background concentration of 10 to the minus 7 for hydroxide ions, it's quite significant, and so therefore we get a basic pH. So it's due to hydrolysis of ClO minus. That's why it's basic. All right. Now, the last little thing that you might be asked for is, well, it has hydrolyzed, so what's the percentage of that? And it sounds scary, and it really isn't. All you have to do is say, well, okay, yes, it did react with water. Let's go back up here. It did react with water. This is how far forward it went, this small amount. So the percent hydrolysis is basically the concentration of HClO at equilibrium over the C0 of ClO minus, the starting stuff. It's saying how far forward has this gone as a percentage. So all we have to do now, let's just move this up a little bit. All we have to do now is say, well, the concentration of this at equilibrium is X. So we're just going to do X over 0.1 and times that by 100%. And since we have our X already, our X is 1.7 times 10 to the minus 4. 1.7 times 10 to the minus 4. Let's move that up. Over 0.1 times 100%. As you can see, it's not very much. Not a lot, but it's enough to make it basic. You know, 10.23, think about the pH scale, it goes between 7 and 14. So 10 isn't amazingly basic, and that's because this isn't really high percentage, but it's enough to definitely make it higher than 7. So that's the process that you want to go through. Each time you always, let's just quickly review, each time you always want to say, what kind of salt is it? Okay, so this one, we figured out this was the salt. We figured out that it was the salt of a strong acid and a strong base. And in this example, the first thing we looked at, we said, what kind of salt is this? Broke it into the two pieces to help us recognize the base and the acid that make it. And then we were able to identify what these two ions are going to do. This one was going to do nothing. This one was going to hydrolyze. And since it's a base, because it has no protons, it has to pick up a proton. So it's a base. We use our Kb for that we get from our Ka in the problem. And we can go ahead and set up our Rice table. And then we can go ahead and find out how far it's gone forwards. So what you want to avoid is ever thinking that the reason why this particular salt has a basic pH in solution is it has something to do with this. It has nothing to do with that. What it has to do with is the fact that this one's conjugate base isn't a spectator ion, it isn't pathetic. So always remember when you're doing these salt calculations, think about what the conjugates are doing, and the way to understand that is to think about what the parents are capable of doing. That will then tell you how strong the conjugates are, or I originally should say how pathetically weak the conjugates are, or if they're just weak. And that will give you the starting point. Once you get to there, pretty familiar territory.